last session, we talked about the coefficient of restitution, which physically signifies that how much amount of the initial relative velocity, what fraction of the initial relative velocity between the colliding bodies along the line of motion, a line of impact, a line of action is restituted back, is regained, is restored. That is what we call coefficient of restitution. Suppose the coefficient of restitution is 0.5. This physically signifies that 50% of the relative velocity between the colliding points along the line of collision is restored. If you drop a ball from certain height h, the coefficient of restitution is 0.5. How high the ball will rise just after the collision? After the collision, the ball will rise up to certain height h dash, and h dash will be obviously half of the initial height, because velocity of approach is v. By energy conservation, we can get that the v equal to square root of 2gh. h is the initial height, and just after the collision, the ball will get a velocity of separation which is equal to half of the velocity of approach, because the coefficient of restitution is half or 0.5. Once you have the velocity just after the collision v by 2, the height will be automatically v square by height h. V square by height g, it's not h. So height to which the body will rise will be different. It's not h by 2. Student generally mistake this, and I would like to take this basic example to explain the idea of coefficient of restitution, and there I will tell you whether we can conserve the linear momentum of the ball in that collision or not. Our traditional example, the easiest example is that the ball is colliding with velocity v naught, say, vertically. A is the coefficient of restitution. Just after the collision, the ball will bounce back with velocity v. Minus of a into u1 minus u2, that is the velocity of approach, equal to v1 minus v2. There is a vector expression. This is what we call Newton's empirical formula, which defines the coefficient of restitution. If this is 1, this is 2, this is 1, this is 2. Minus a, u1 is minus v naught j cap. This point is at rest of the ground, therefore u2 is 0. Since the ground is at rest, v2 will be equal to 0, and v1 we assume it up vj cap. Using the Newton's empirical formula, the final velocity just after the collision will be equal to a into v naught. Find v. Find the energy loss during collision. The energy loss during collision is the kinetic energy loss. Because during collision, this body is not changing its height, it's not changing its potential energy. The change in kinetic energy is always final minus initial. The final kinetic energy is half mv square. The initial kinetic energy is half mv naught square. Half m you take common, v naught square you take common, v by v naught square minus 1, and v upon v naught is equal to E. So you are getting minus half mv naught square 1 minus E square. Change in kinetic energy is negative because E is less than 1. E can never be greater than 1. At best it can be 1. And that collision is said to be perfectly elastic. Negative sign signifies that the kinetic energy is lost. So loss of kinetic energy is equal to half mv naught square to 1 minus E square. Energy loss. Loss means negative. Itself is negative. You can impose second question, a third question. First question is the velocity just after the collision. The second question is the energy loss during the collision. And third question, how high will it go? If it is released from certain height h, if initial height is equal to h, or this parameter, the given data, you can find the final height, let it be h dash, let it move to this position. So the vertical distance, let it be h dash. H dash equal to b square upon 2g, and b is equal to a into v naught upon 2g. So in E square into v naught square upon 2g, and v naught square upon 2g we can write it is h. So h dash equal to E square into h. If we assume E equal to half, h dash is equal to half square of this h by 4, but not h by 2. V equal to E into V naught, that's equal to V naught by 2. But h is not equal to h by 2, rather it is h by 4. So general formula for this, when the body is dropped from certain height h, after the first collision, it can attain a maximum height h dash, which is equal to E square time h, not E time h. Whereas the velocity of the body just after the collision will be equal to E times h, whereas the maximum height just after the first collision or after the first collision will be equal to E square time h. With this conceptual example, we can design some more interesting examples. The idea behind this example is Newton's empirical formula. The velocity of approach and the coefficient of extrusion, negative of that is equal to velocity of separation. So we will get B equal to E into V naught. Under this assumptions that the body will fall, move vertically, and the ground or the surface is at rest, and the final height you can call h dash or h1, maximum height attained after the first collision will be equal to, yes, how much? A square into h, not E into h. Similarly, we can prove that height, maximum height after the second collision will be equal to a square, square of this into h, that is e to the power 4 into h, and after nth collision the maximum height attained by this body will be equal to e to the power 2n into h. Using this idea, let us solve some more interesting problems. We are solving some problems by using the coefficient of restitution formula, that is Newton's empirical formula or impact formula, which states that the velocity of approach into minus of the coefficient of restitution in vector form is equal to velocity of separation. Let us take the previous example and ask few more questions. The question is, when the body is released from certain height h, it collides first time with the velocity v naught is equal to square root of 2gh. By using kinematics, you can get it, everybody knows this. Since the coefficient of restitution is E, the fraction of the relative velocity along the line of impact, that is the vertical direction, will be back, that is equal to E into V naught. With this velocity, it will go to a certain height and come back before experiences second impact. With the same speed. Just after the second impact, its speed will be equal to A into V1 and V1 is equal to A into V naught, E square into V naught. Similarly, after nth impact, the velocity of the body just after the nth impact will be equal to Vn is equal to e to the power n into V naught. By logic you can understand. We can calculate the velocity just after the first impact, e to the power 1 into V naught. Just after the second impact, e to the power 2 into V naught. Therefore, logically you can conclude that just after the nth impact, the velocity of the body will be equal to e to the power n into V naught. Find the total time of motion. Find the total distance covered till the body stops bouncing. To solve this example, we need to calculate the time during the initial position and the first collision. During the first collision and second collision and third collision, I have taken all the collisions separately at different points. In fact, all the collisions will take at the same place. But for the sake of simplicity, I have exaggerated this figure. From here to here, let the time be t1, or you can write t0. That's equal to 2h by j square root. You can obtain this formula by applying s equal to u plus r square. Everybody knows this. From here to here, the time let be t1. This is t0. This is t2. But in the first and the second collision, the time interval is let be t1, and that's equal to v1 upon g. v1 equal to a into v0 to e v0 by t0. You can write as from here to here. If you just write v equal to u plus at, here u is 0, a is minus j, and v is minus v0. So you can just write t0 is equal to v0 upon g. This you can write directly v0 upon g, where v0 equal to 2gh. Therefore, t0 can be written square root of 2h upon g, or directly you can write h equal to half g t0 square. Well, next, t1 equal to 2e into v0 by j. The time interval between the second and the third collision will be equal to t2. That's equal to v2 upon j, but v2 equal to 2 e square into v0 upon g, and so on. Adding all the times till countless, innumerable collisions take place. The total time can be written as t is equal to t0 plus t1 plus t2 plus t3, and so on. So t0 equal to v0 by g, t1 equal to 2 into v0 by g, t2 equal to 2 square v0 by g, and so on. You can take common v0 by g, 1 plus 2 e, 1 plus e plus e square plus e cube. So this is a geometric progression, and its sum can be calculated by using the formula 1 by 1 minus e. So you will get 1 minus e plus 2e, that is 1 plus e by 1 minus e into v0 by g, where v0 is equal to square root of 2gh. So this will be 1 minus e, 1 plus e upon 1 minus e to h by g, because v0 is equal to, because v0 is equal to square root of 2gh. In this way, we can find the total time of motion till it stops bouncing. It will stop bouncing after countless innumerable impacts or collisions. Using this idea, We can also calculate using this idea. We can also calculate the total distance. The distance it is covering from this point to this point till the first collision. It covers a distance. How much? d1 is equal to h. Between the first and second collision, the total distance will be this plus this. h1 plus h1 to h1. During the second and third impact, it covers a distance h2 plus h2 to h2 and so on. Then the total distance covered is given as d equal to d1 plus d2 plus d3 and so on. d1 equal to h, d2 equal to h1, d3 equal to h2. But we do not know h1, we do not know h2. But that I explained in the last example that the height attained by the particle after n collisions is equal to e to the power 2n into h. In this way you can write, after the first collision, the height attained is h1 equal to e to the power 1 into h. After second collision, it will attain maximum height, it will be 2 into h. The third collision, it attains the height, it will be 4 into h. And the things will proceed like this. So here you can take common h into 1 plus, you take 2 common, 1 plus, this is h, h1 equal to e square h, h2 equal to e to the power 4h, h3 equal to e to the power 6h. If you take h common, you are getting 1 plus 2 e square take common, 1 plus e square plus e4 plus e6 and so on. Infinite geometrical series again. So to take the sum of this infinite series, geometrical series, a by 1 minus r, the common factor, that is a square. So you are getting 1 minus a square plus 2 square, that is 1 plus a square by 1 minus a square into h. So this is the total distance covered by the body till it stops bouncing. Then they may ask you to calculate the average speed. If you want to calculate the average speed, you can just write the formula for the average speed, that is the total distance upon the total time. And by evaluating this, you can get the average speed. Sometimes they may ask you to calculate the average velocity. In velocity, what is used? You can write its formula. Average velocity is equal to net displacement, or the total displacement upon total time. When it stops bouncing, it will come to rest at the same spot. Because I have exaggerated this figure for the sake of clarity. All the impacts, all the collisions will take place at the same spot here. So this is the net displacement. This is equal to minus h into j cap. So net displacement is equal to minus h j cap upon t, and you can substitute the value of time t to get the average velocity. Next, we would like to calculate the thrust exerted by the ground on the ball during each collision, and multiply that thrust, the average thrust, with the time of impact to get the impulse of that thrust, and that impulse is numerically equal to the change in momentum of the ball during that collision. In the first collision, the ball is changing how much momentum? In second collision, the ball is changing how much momentum? In this way, if you go on adding the change in momentum of the ball in all collisions, that will give you the total, the cumulative of the change in momentum, and that's numerically equal to the change in momentum of the earth, or momentum delivered to the earth, or momentum delivered by the earth to the ball. That's a great question. Taking as a separate bit, I would like to discuss this. Find the momentum delivered to the earth by the colliding ball during the first collision, during second collision, during third collision, we need to calculate the momentum change of the ball. This is the first collision, this is the second collision, the third collision, and I have mentioned the velocity of the ball just before and after, just before and after, just before and after the impact or collision. And this will continue. To start from this first collision. During first collision, change in momentum of the ball is equal to final momentum minus initial momentum. Final is how much? Plus m, or you can just write plus m v1 j cap minus m v naught j cap. That will be equal to m v1 plus v naught. v1 equal to a into v naught. Therefore, del P1 is equal to m v naught 1 plus e in j cap direction. Similarly, during the second collision, how much momentum is changing for the ball? Final momentum minus initial momentum. The final momentum is how much? M square v naught j cap. Directly I am writing the final velocity, that's the initial velocity, minus, since it is moving down, the initial momentum is downward, m into v naught into minus j cap. This will give us m v naught into A 1 plus E j cap. This is over. Now take third collision. During third collision, the change in momentum of the ball is del P3. That's equal to its final momentum minus its initial momentum. Its final momentum is equal to m eq v naught j cap minus m e square v naught j cap. This gives us m v naught into e square 1 plus e j cap. After doing 3 turns, momentum change during first collision, momentum change during second collision, momentum change during third collision. We can see some common factor, m v naught and 1 plus e. Here m v naught 1 plus e, here m v naught 1 plus e, and some additional factors. This is a square and so on, e cube, e4 and so on. The momentum delivered to the earth during first collision is equal to change in momentum of the earth during first collision. Since the earth and the ball is an isolated system, no net force is acting on the earth and ball system. Therefore, we can conserve the momentum of earth plus ball system. This will be explained in detail in the next context. Here, you can understand that how much the ball is changing its momentum, that much momentum will be changed by the earth in opposite rates. So, momentum delivered by the ball onto the earth is equal to change of momentum of the earth, that is numerically equal to the change of momentum of the ball. So, the momentum delivered to the earth by the ball during the first collision will be equal to del P1. Momentum delivered by the ball during the second collision to the earth will be equal to del P2. In this way, if you go on adding all this, the momentum delivered during the net momentum delivered, the total momentum delivered during all collisions is given as the sum of all the change in momenta of the body during respective collisions. Momentum delivered. Del P1 is equal to m v naught 1 plus c. Del P2 will be equal to m v naught into 1 plus c into v naught into e. So, if you take this factor common, 1 plus e plus e square plus e cube and so on. So, m v naught 1 plus e, this will be 1 by 1 minus e. So, we will get the momentum delivered in which direction? The change in momentum of the ball is happening in positive y direction. Therefore, the change in momentum of the earth will be happening in negative y direction. So, momentum delivered to the earth physically understood to be downward, negative downward. M v naught 1 plus a by 1 minus e. That's a nice problem. E is the coefficient of restitution. After this problem, I think you understood the meaning of coefficient of restitution and Newton's empirical formula. It will be helpful for us to proceed for solving the general problems of head-on collision and oblique collision. And before that, we would like to re-explain the conservation of linear momentum during the process of collision in this context. Well, we have completed the first 5 concepts, first 5 contexts we have already discussed. Let us now focus on the possibility of conservation of linear momentum of the system of 2 particles, 2 colliding particles. If you take 2 balls moving in any arbitrary directions with velocities u1 and u2 respectively, bearing the masses m1 and m2 respectively, just before the collision. During the collision, let they interact by the impulsive forces F and minus F. If you take it F, this will be minus F. If you take it as F, this will be minus F. Or you can take it F1, you can take it F2. F1 plus F2 vector, both when you add, you will get 0 because they are action reaction pair according to Newton's third law. If you take M1 as a system, this is the force acting on M1 during the collision. This is the force acting on M2 during the collision. So these 2 forces are impulsive forces which can change the momentum of the bodies significantly. For the sake of simplicity, we disregard the effect of non-impulsive forces such as gravity. On each body, the net force acting is not equal to 0. Therefore, each body must change its momentum. M1 changes its momentum from M1 U1 to say M1 B1. It will move in this direction with this speed, say, and M2, let's change its momentum from M2 U2 to M2 V2. We have our equation, impulse momentum equation, that is none other than Newton's second law in integral form. Impulse momentum equation states that the net impulse is equal to change in momentum. This is our acting formula now. When you apply this formula on the first object on M1, how much force is acting? Minus F. What is its impulse? We do not know in which way this force is changing with respect to time. If it is so, we can take its impulse. Impulse of the force acting on M1 is equal to change in momentum of the first body, that is del P1. On M2, if you apply impulse momentum equation, What is the net force acting on the body M2? Let it be F. Its impulse, that the net impulse acting on the body 2 is equal to change in momentum of the body 2. When we add these two equations, this will get cancelled. And we are left behind with these two terms in right hand side, which signifies that the change in momentum of the first body plus change in momentum of the second body is equal to 0. This is called conservation of linear momentum of the system of particles. For the sake of simplicity, we have taken two particle system. When they are colliding, the net momentum of the system remains conserved. Which tells that whenever the net external force acting on the system of colliding bodies net external force acting on the system of colliding body is 0. The net impulse will be equal to 0. Then the total momentum of the system remains conserved. This is what is called conservation of linear momentum. Conservation of linear momentum. And using this idea, let me demonstrate few conceptual examples. Example is, two balls are colliding in mid-air. Two balls collide in mid-air. Explain the possibility of conservation of linear momentum. Explain the possibility of momentum. Unless it is specified, momentum means linear momentum, or else it will be angular momentum. Explain the possibility of momentum conservation. When they are colliding in the mid-air, the impulsive forces are equal and opposite. In addition to the impulsive forces, we have the gravity. Acting on both the bodies. And these forces are called non-impulsive forces. So, the net impulse is equal to everything integral plus minus everything integral plus m1 j dt, integral of these two forces. This is the net impulse. This is the system. System of two colliding particles. The net impulse is equal to impulse of the impulsive forces, impulse of the impulsive forces, their action reaction pair, therefore this will be 0 as a whole, get cancelled, is equal to m1g and m2g are constant quantities, you can take them out. The time of collision is very small. So m1j plus m2j into del t. Since del t is extremely small, what is del t? Time of collision. The bodies are in contact for a very, very extremely small time. Since del t is very, very small, this product can be approximated to 0. Hence, net impulsive window is not exactly equal to 0, can be ignored. During what time interval? During the time of collision. Hence, we can conserve the linear momentum of the system during collision. Just before the collision, the momentum of the system can be approximated to momentum of the system just after the collision. Try to understand. You can conserve the momentum, the possibility is there, but that is limited to the time interval in which the collision takes place. These two momenta can be equalized during the collision. Just before the collision, just after the collision, you can equate the momenta of the system. However, if you take a finite time or considerably long time compared to the time of impact, just after the collision, if you think that they will lose contact and they will fall under gravity, what will happen? Always this force will be absent thereafter. However, this force will continue to be present. And when the time interval is more, say 1 second, 2 seconds, 3 seconds and so on, we cannot ignore this portion. In other words, we can say that the finite gravitational forces, the non-impulsive forces can change the momentum of the system significantly during a considerable long time. Therefore, we can conserve the linear momentum of the system while they are falling. During a long time, in free fall, we cannot conserve the linear momentum because the gravitational force acting on the system, that is m1 plus m2 into g into dt, is not equal to 0. Cannot be ignored because del t is finite. Here del t is infinitely small. So we have discussed the possibility of conservation of linear momentum of these two colliding balls. During collision, we have the possibility of conserving the linear momentum of the system. Just before and after the collision, you can conserve the momentum, disregarding the effect of gravity. However, after the collision, they will fall freely. If you take this entire system, you cannot conserve the momentum of the system because the gravity will change the momentum of the system. Very nice, interesting conceptual question to clarify the idea of conservation of linear momentum. Whenever no external force acting on the system, we can conserve the linear momentum of the system. Or even though, let us take another example, which is a block connected by a spring, light spring, which is fitted with this vertical wall. A bullet comes and hit the stationary block with some velocity. If we ignore the friction between the block and ground and take this as a system, bullet plus block. This is a system of two particles, bullet one particle, block another particle. During collision, on the bullet, a reaction force acts, impact force acts due to the block. When the bullet goes into, penetrates the block will offer some resistance. The resistive force or the frictional force is the impulsive force here. Let it be F. And the impulsive force acts on the block in opposite direction minus F. During the time of the collision, when the bullet gets into the block, travels some distance with respect to the block or inside the block, the spring also will get compressed little bit. The spring is compressed, the compressed spring will start pushing it. In this way, you take this as a system, the net force or net impulse, net force is equal to spring force plus F plus minus F. This will get cancelled. Therefore, the spring force is the net force acting on the system. The impulse of the spring force is spring force its average value into the time of collision. First of all, we have to see that the spring force has a magnitude that's equal to K into X. That is in accordance with Hooke's law, where X is the deformation. It may be compression or it may be elongation. In this case, it is compression of the spring. During a very small time of collision, the spring will get compressed very little. The deformation of the spring is very small. Therefore, the spring force is very small. since the time of collision is very, very small, the impulse of the spring force, that is the product of the spring force and the time of collision, that is the net impulse, will be extremely small quantity, which can be equated to 0. In this way, we can conserve the linear momentum of the system just before and just after the collision. During the collision, you can conserve the linear momentum of the system. But after the collision, what will happen? The bullet will penetrate the block and it stops with respect to the block. After that, both the bullet and the block will move with some velocity and the compression of the spring will be significant. The spring will be compressed more and more. Therefore, the spring force will be more and more. And the time of interaction of the system with the spring will be more and more. Therefore, the spring force into the time of interaction will be a great thing. Great quantity, cannot ignore this quantity. Thus, the momentum of the system cannot be conserved during the long time interval after the interaction of the bullet with the block. The combined system, the combined mass will move towards left for some time, and during that time you cannot conserve the linear momentum of the system due to the significant impulse of the spring force. However, during the collision of the bullet with the block, the time of collision is so small that the spring force is extremely small, and when you take the product, this will be infinitely small quantity or exceedingly small, or we can ignore it to conserve the linear momentum of the system. That's a very interesting thing. You can also take little bit friction. Even though little bit friction is there, you can take the frictional force when it tends to move towards left, frictional force will act towards right. If you take the impulse of the friction, the frictional force, even though there is a finite force, still then this time factor during the collision is extremely small. So a finite quantity into extremely small quantity is also very small and can be ignored. These are very interesting thing, very subtle thing to analyze, in which the net force acting on the system is not exactly equal to 0, but the impulse of the net force acting on the system is so small that during that time period we can ignore it and will be able to conserve the momentum of the system or equate the momentum of the system just before and just after the collision, just before and just after that time interval. Case to case basis, we have to test whether we can conserve the linear momentum of the system or not. In next class I will tell you the head-on collision between two objects, and we will take these two ideas into account and solve the problems of head-on collision and oblique collision of the objects.